The Hawking-Brewer hypothesis, the secret link between black holes and the Big Bang. This video explores Stephen Hawking's theory of the link between black holes and the birth of the universe, the Big Bang. Could our universe be part of a black hole explosion in the past? The cosmos is a tapestry woven with mysteries, questions that stretch the imagination and challenge the very foundations of our understanding. Among these, few are as profound as the origins of the universe itself. What caused the Big Bang? Where did all the matter and energy come from? And what secrets do black holes, those enigmatic cosmic abysses, hold about the ultimate fate and birth of everything we know? In the early 1970s, two brilliant minds, Stephen Hawking and Brandon Carter, joined later by James Bardeen and others, began to ask questions that would bridge the gap between two of the most extreme phenomena in physics, black holes and the Big Bang. But it was Hawking, with his singular vision and relentless curiosity, who would push these ideas to their logical and sometimes radical conclusions. Hawking's work, often in collaboration with mathematician and physicist Jim Hartle, and inspired by Roger Penrose's singularity theorems, led to a hypothesis that would challenge the boundaries between the beginning and the end, between collapse and explosion. This is the Hawking-Brewer hypothesis, the suggestion that the birth of our universe, the Big Bang, might be connected in a deep and secret way to the physics of black holes. To grasp the profound implications of this idea, we must first understand the two protagonists, the black hole and the Big Bang. A black hole is formed when an immense mass collapses under its own gravity, compressing into a point of infinite density known as a singularity. Around this singularity lies the event horizon, a boundary beyond which nothing, not even light, can escape. For decades, black holes were considered cosmic endpoints, places where matter and energy disappear forever. The Big Bang, on the other hand, is the event that marks the birth of space, time, matter, and energy. According to the standard cosmological model, everything in the universe was once compressed into a single, infinitely dense point, a singularity, before exploding outward in the grandest event imaginable. The universe as we know it began its expansion from this singularity around 13.8 billion years ago. At first glance, black holes and the Big Bang seem like opposites. One is an endpoint, the other a beginning. But Hawking and others noticed something remarkable. The mathematics describing the singularity at the heart of a black hole is strikingly similar to the equations that describe the singularity of the Big Bang. Both represent regions where the known laws of physics break down, where densities and curvatures become infinite, and our current theories, general relativity and quantum mechanics, cease to be predictive. Here Hawking saw a tantalizing possibility. What if, instead of being mere mathematical coincidences, these singularities were fundamentally linked? Could the birth of a universe be, in some sense, the reverse of a black hole's death? Let us journey deeper into the heart of the hypothesis. In the 1970s, Hawking, along with George Ellis and Roger Penrose, developed the singularity theorems, which showed that under certain conditions, singularities are inevitable in general relativity, either at the origin of the universe or at the core of a black hole. These singularities are places where space and time themselves come to an end, and the curvature of space-time becomes infinite. But Hawking's curiosity went further. He asked, what happens beyond the event horizon of a black hole? And more provocatively, could a new universe actually be born inside a black hole? Some cosmologists had speculated that a black hole's singularity might not be a simple endpoint, but a bridge, a sort of cosmic wormhole, to another region of space and time. In this view, the collapse of matter into a black hole could, on the other side of the singularity, be seen as a kind of cosmic bounce, giving birth to a new, expanding universe, a baby universe disconnected from its parent. Hawking refined this idea with his no-boundary proposal, developed with Jim Hartle. They suggested that at the very beginning of the universe, time itself could be thought of as curving smoothly into space, eliminating the traditional singularity. The universe, in this view, would have no boundary, no edge, no singular starting point, just as the surface of the Earth has no edge or boundary. This elegant mathematical model replaced the singularity with a smooth, finite geometry, sidestepping the infinities that plague both the Big Bang and black holes. But what about the link between black holes and the Big Bang? The Hawking-Brewer hypothesis suggests that the processes governing black holes and the origins of the universe might be two sides of the same cosmic coin. Instead of thinking of black holes as the ultimate graves of matter, they might be seen as cradles, seedbeds for the birth of new universes. In this bold vision, every black hole could be a potential Big Bang for a new universe, with its own space, time, and physical laws budding off from our own. Consider for a moment the implications. Our universe, with its billions of galaxies and vast stretches of space-time, could itself be the offspring of a black hole in a parent universe. In this scenario, the Big Bang was not the ultimate beginning, but rather a transition, a transformation of matter and energy from one universe to another through the crucible of a black hole singularity. This idea is not merely speculative whimsy. It arises naturally from the mathematics of general relativity and quantum theory, especially when considering the so-called information paradox. Hawking himself famously struggled with the question, what happens to information that falls into a black hole? According to classical physics, it is lost forever, but quantum mechanics insists that information must be preserved. If black holes are in fact seeds for new universes, perhaps the information swallowed by a black hole is not lost, but simply transferred, encoded in the birth of a new cosmos. The laws of physics, the constants and parameters that define our universe, might be inherited from a parent universe through black hole reproduction. This opens the door to a kind of cosmic natural selection, a hypothesis championed by physicist Lee Smolin, in which universes that are more efficient at forming black holes give rise to more offspring universes, propagating their physical characteristics across the multiverse. But how does this cosmic generational process work? Imagine at the heart of a collapsing star, a singularity forms, a point where densities and curvatures soar to infinity. In classical general relativity, this is the end of the story. But if quantum gravity, our unfinished theory combining quantum mechanics and general relativity, intervenes, it might prevent the formation of a true singularity. Instead, at the smallest scales, space-time could bounce, leading to the birth of a new region of space-time, a new universe, expanding away from the singularity on the other side. From the perspective of an observer inside the new universe, this event would appear as a Big Bang, a sudden, hot, dense expansion. From our vantage point, it is a black hole, a mysterious object from which nothing returns. In this way, the death of a star in one universe becomes the birth of a cosmos in another. This vision leads to a dizzying array of possibilities. If every black hole spawns a new universe, the multiverse could be a vast branching tree, with each universe giving rise to countless others through the formation of black holes. The constants of nature, such as the strength of gravity, the mass of the electron, or the cosmological constant, could vary from universe to universe, shaped by the conditions in their parent universe's black holes. In this cosmic family tree, our universe is both the child of a previous universe and the potential parent of countless others. The Big Bang is no longer an absolute beginning, but a transformation, a node in the ever-branching network of reality. Of course, these ideas are speculative, and many questions remain. One of the greatest challenges is the lack of a complete, experimentally tested theory of quantum gravity. The physics of singularities, both in black holes and the Big Bang, remains shrouded in mystery, accessible only through the most abstract mathematics. Yet tantalizing hints have emerged from modern research. For example, recent developments in string theory and loop quantum gravity suggest that space-time is not infinitely divisible, but made up of tiny, discrete atoms of space and time. In these models, singularities are avoided, and space-time can undergo bounces, collapses followed by expansions. The Big Bounce replaces the Big Bang, and black hole singularities become gateways rather than endpoints. Moreover, the discovery of Hawking radiation, Stephen Hawking's most famous contribution, showed that black holes are not truly eternal. They slowly evaporate, emitting particles and losing mass over vast timescales. This process raises deep questions about the fate of information and the ultimate nature of space-time. If black holes can evaporate, could their interiors be connected to other regions of the cosmos? Could the information they contain seed new universes? The Hawking-Brewer hypothesis is not a single definitive theory, but rather a web of interconnected ideas, an invitation to reimagine the relationship between the beginning and end, collapse and creation, death and birth. It encourages us to see the universe not as a closed system with a singular origin, but as a dynamic, evolving network of interconnected realities. In this view, the ultimate origin of our universe is not an inscrutable singularity, but a link in a cosmic chain, a cycle of creation and destruction, of black holes and big bangs, stretching back into the infinite past and forward into the infinite future. But what evidence might support or refute this grand vision? The challenge is immense. By their very nature, black holes hide their secrets behind event horizons, and the earliest moments of the universe are shrouded in the cosmic microwave background, a faint afterglow that tells us only part of the story. Yet physicists continue to search for clues. One avenue of exploration is the study of cosmic inflation, the rapid expansion of the universe in its earliest moments. If our universe was born from a black hole in another universe, subtle imprints might remain in the distribution of galaxies, the polarization of the cosmic microwave background, or the properties of primordial gravitational waves. Advanced telescopes and experiments, such as the James Webb Space Telescope and future gravitational wave detectors, may one day uncover hints of these ancient connections. Another approach is the study of quantum information and the so-called holographic principle, the idea that the information content of a region of space can be described by a theory living on its boundary. This principle, inspired by the physics of black holes, suggests a profound unity between gravity, quantum mechanics, and information theory. If true, it could provide the mathematical scaffolding for understanding how information passes from one universe to another through the birth and death of black holes. Perhaps the deepest implication of the Hawking-Brewer hypothesis is philosophical. It challenges our notions of beginning and end, causality and destiny. If every black hole is a potential universe, and every universe emerges from a black hole, the cosmos is an endless cycle of creation. There is no ultimate beginning, no final end, only transformation. This vision resonates with ancient philosophical ideas, the cosmic cycles of Hindu cosmology, the ebb and flow of existence in Buddhist thought, the eternal return of the Stoics, yet it is grounded in the most advanced mathematics and physics of our time, a testament to the power of human imagination and curiosity. As we ponder these possibilities, we are reminded of Stephen Hawking's own words, "Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious." The Hawking-Brewer hypothesis invites us to look up, to wonder, and to question. It reminds us that the universe is stranger and more wondrous than we can imagine, that black holes, once thought to be the tombs of matter and energy, may instead be the wombs of new universes, birthing realities beyond our wildest dreams. In the end, the connection between black holes and the Big Bang is not just a scientific puzzle, but a cosmic story, a narrative that links our origins to the deepest mysteries of existence. It is a story still being written in the equations of physicists, the observations of astronomers, and the imaginations of all who dare to dream. So the next time you gaze at the night sky and marvel at the vastness of the cosmos, remember, our universe may not be alone. It may be part of a grand, interconnected family, a cosmic multiverse born from the secret link between black holes and the Big Bang. The answers may be hidden in the darkness, waiting to be discovered by those who continue to ask the biggest questions of all.